Today we discuss section 19, derivatives. First we have seen the definition. This is same as the definition what you have discussed in your real analysis class. The only difference is this function f is complex functions rather than the real function. Let f be a function whose domain of definition contains a neighborhood mod z minus z naught less than epsilon of a point z naught. In order to discuss the derivative of a function f at z equal to z naught, there should exist at least one neighborhood about z naught which is fully contained in the domain. Then the derivative of f at z naught is the limit f dash z naught equal to this is usually d by dz of f of z at z equal to z naught. So the symbol is f dash of z naught. That is equal to limit z tends to z naught f of z minus f of z naught divided by z minus z naught. For the same quantity f dash of z naught, you can use another formula, limit h tends to 0 or some small distance, a small difference h, or you can write it as delta z. You can consider it as delta z tends to 0. You can write this as f of z plus delta z naught plus delta z plus minus f of z naught minus f of z naught divided by delta z. This is also the same definition for derivative. So f dash z naught, or the derivative of f at z equal to z naught, is defined as this limit. We usually use this formula to denote f dash z naught. There is a remark: the function f is said to be differentiable at z naught when this f dash z naught exists as a finite complex number. If we look at this definition geometrically, you can consider this xy plane as the domain of f of z containing a point z naught, and we can write this this distance as modulus of z naught, and if we write this any arbitrary z, we can consider this as z. Then this distance is what we call delta z. Okay, this is what we call delta z. This is delta z, or you can write delta z as this is our, if you consider this a vector, then you can easily write delta z as z minus z naught, z minus z naught. Now if you consider this limit, what is the meaning of this limit, or these both these limits are equivalent? By substituting z minus z naught as delta z, you will get this formula. So if you consider both these limits, then you can understand that as this delta z tends to 0, that means this difference tends to 0, or equivalently z tends to z naught. Okay, so we will discuss the limit for which this z tends to z naught, then the difference between this quotient f of z minus f of z naught divided by z minus z naught. So that should be a finite quantity. That is the meaning of this limit. Okay, so in order to discuss this, we should verify that there should exist a epsilon neighborhood which is fully contained in the domain of the function f. Suppose this is the domain of the function. Okay, so in this remark, what I have to discuss is if we replace this numerator or equivalently this numerator, and I put it as delta omega. Okay, delta omega is f of z plus z naught minus f of z naught, or this quantity. So if you write this numerator as delta omega, Then what is the definition of f dash of z naught? F dash of z naught, usually we denote this as d omega by dz, where we represent omega as f of z. If this is the function, then f dash z naught is represented by d omega by dz, and that is equal to limit z tends to 0. If we use this delta z tends to 0. If we use this formula, delta z tends to 0, and numerator can be replaced by delta omega and divided by delta z. So we use this formula as well to define to denote f dash of z naught. Now we are going to discuss an example. If we consider f of z equal to z square, then how will you verify this f is differentiable at an arbitrary point z naught? For that, we consider f dash of z. Okay. We need to verify the existence of this at every point z. Then by definition, f dash of z is limit delta z tends to 0 delta omega by delta z. Okay, so this is the definition of f dash z. Now you write this delta omega is equal to f of z plus delta z. We didn't use z naught because we need to find out f dash of z at an arbitrary point. So for a fixed point z, we write the formula. Okay, delta omega is f of z plus delta z and f of z. Okay, now you apply the definition of f of z. Delta omega will be z plus delta z whole square, because f of z is given as z square. So f of z plus delta z is this square, and f of z is equal to z square itself. Okay, so if we consider the difference between these two quantities, this is in fact if you consider the term by term multiplication, so the first term will be a plus b whole square, then you can easily cancel out this z square. So the second term onwards you can have this the second term onwards, so that will be 2 times z times delta z, and one more term is there, delta z square. Then we have the denominator whole divided by in order to write the derivative, we need to get the formula first. F dash of z, which is equal to limit delta z tends to 0. Delta omega is the numerator, that is what we have simplified here. So that is 2 times z delta z plus delta z square divided by delta z. Once you simplify the quotient here, you will get limit delta z tends to 0, then that will be 2 times z plus delta z. Okay, by cancelling this delta z from both terms of the numerator, and you will get 2z plus delta z. By putting delta z equals 0, you will get the answer as 2z. Okay, we all know what is the derivative of z square, that is 2z. So this is why we consider the definition is the same way we find the derivative of a real function, or using the first principle or definition, you can carry out the same thing in the complex analysis as well. Okay, so there are some examples, or other examples are discussed in the textbook, so please go through it. So once I'll discuss one more example, because this is the what example 1 says that f has a derivative at z equal to every point of the complex plane for the function f of z equal to z square. Now I am going to discuss another function f of z equal to z conjugate. Okay, once you consider this, then once you try to find out the derivative of this function as f dash z, which is equal to limit delta z tends to 0. In fact, this is f of z plus delta z, that is z plus delta z whole conjugate minus f of z, that is z conjugate itself, divided by delta z. So simplifying, you will get this is limit z tends to delta z tends to 0, and the numerator will be the z plus delta z whole conjugate is z conjugate plus delta z conjugate. We have seen the properties of conjugate. Then this will be z conjugate plus delta z conjugate, minus we have minus delta minus z conjugate divided by delta z. So now you will get limit z delta z tends to 0. This will be delta z conjugate divided by delta z. We already discussed this limit in the previous class in the section of limits. Limit z tends to 0 z conjugate by z. So that limit does not exist, because if we try to find out this limit through real axis, you will get the value as 1, and if you consider the same limit through imaginary axis, that limit will be minus 1. So in fact the limit does not exist for this function. So we can say that limit delta z tends to 0, delta z conjugate by delta z does not exist. We have, therefore we have f dash z, okay, does not exist. So this is the definition of derivative of a complex function. So in order to say that a function is differentiable at z naught, we have to get this f dash at that point z naught. Okay, so now there are some other examples are discussed in the textbook, so please go through it. And next we discuss some properties of this differentiation. We know that in real analysis there are a number of formulas or identity for this differentiation, such as some derivative of sum of functions is sum of its derivatives. So product rule and quotient rule and everything is there in real analysis. The same rules will be held in complex analysis as well. So I'm not going to prove all these properties of complex function, derivative complex functions. So please go through it. All the properties are given in the textbook. And one thing you should remember is the chain rule is also held in the complex analysis as same as the real analysis. So I just mentioned that rule. If this function small w is equal to, I can put it as some remarks. Okay, remarks. If w is equal to small f of z and capital W is equal to capital F of z, then chain rule says that d capital omega by dz. In fact, this w is not a function of small z. Okay, so that is a if you consider this is the I put it as this g, so I can write this is in fact capital W is equal to some g of omega. So omega is a function of f of z and g is a function of omega. Okay, so this w or this capital W can be considered as a function of z. That is because if you put this omega is equal to f of z, then this is g of f of z. So this w can be differentiated with respect to z. So how will you differentiate this w? Exclusively this w is a function of omega. So first we write dw by d, this is capital W, this by omega, and we multiply it with dw by dz. These two derivatives can be easily evaluated from these two equations. Okay, so this dw by dz is equal to dw by d omega by dz. Okay, so this is the same rule what we have used in the real analysis classes. So please remember this. And there are some examples, elementary examples are given for illustrating these rules, such as sum rule, product rule, quotient rule, and chain rule, etc. So please go through it. And this is all the way up to section 19, derivatives. Okay, so next class we will discuss some properties of derivatives, and some interesting functions which have nice behavior in complex plane, for which this differential is essential. Okay, thank you.